Okay.
Everybody would love that.
Yeah.
What is this? Okay, so this step is slow. This step is fast. Let's start off by earning some smiley faces. So, on your own, without your table buddy, okay, write me the rate law for each step. Where'd it go?
Okay.
Huh? You don't need it. This is just what we did on the quiz. Write a rate law from an elementary step. You got it.
Oh, yes. Smiley faces coming away.
All right, if you have that, you can have a smiley face for each.
Oh, yes.
Okay? So when it's a mechanism and you have the steps, right, it's just based on the stoichiometry of the problem. Okay? Now, let's determine the overall. Okay? So first let's write the overall reaction because it's not given. So the overall reaction means we cancel out intermediates and spectators. Okay, so NO3 cancels out, and what would that be classified as? Intermediate, yep. And then one of the NO2s cancels, and that is classified as that's a catalyst. All right, carry what's left down. So we have NO2, CO, changing into NO and CO2. Now, we want to write the rate of the overall reaction. Now, let's note what we can't do. You don't just look at the stoichiometry. Why not anymore? Because it's not, this is not an elementary step. It's the overall. But we said, what is the step that really determines the rate? The slow step. So the overall rate is the rate of the slow step. So the slow step is the rate of the overall reaction. Because once you think of it like this, right? If I were to draw a graph, the slow step's first, which means the first hill's really big, and then the second hill's little. Okay? If this is a roller coaster, it's going to take energy to get up this first hill. Does it take any energy to get over that hill then? No. Once you get past the slow step, it just flies through. Question, Connor?
Oh, I was gonna ask why it wasn't things added together, but it's just like the residual energy.
Yes.
What
Yeah.
if it's the other way around? Then wouldn't it also take energy to get to the slow?
So you're saying if the slow step is first,
Yeah.
hold that for 2 minutes, and then we'll talk about that example, because it does change it. Yes. Yes, Sam.
Okay, this probably, okay, if your slow was the second rate, would you still write that as a rate even though you don't have an NO3?
So the slow step is always going to govern the overall. But when the slow step comes second, there's something else we're going to have to do with it as well. But if the slow step is first, it's literally the exact same thing. So we'll do an example of one of those here in a second. Yeah, what's up?
What would it look like if you did a graph with the x-axis being time? Because all of these graphs are in time as far as like
No, they're just progress.
progress.
So it's just as it's proceeding.
So if it was time, would it just be like energy? And time?
Yeah, you don't really ever, I don't know if I've ever seen a graph where you compare energy and time. Because because the energy is constantly changing, you know? It would look, I guess, kind of somewhat similar. because the energy goes up as time progresses. So it's kind of time, but it's not a direct measurement of time. So I'll think about that though. I don't know if I've ever seen one where it's truly a time measurement, meaning like seconds or minutes or something like that. So, any other questions on that so far? Okay, for smiley face with your table buddy, answer practice 5.8. Ready, go. If you could, once you have a final answer, if you could circle it for me, so as I walk around, I just know. It's part of the overall reaction. Okay, give me a wave if you need any more time. All right, the answer you should have on your paper is for the overall rate. Is that NO? If you have that, you can have another smiley face. Questions on that? Okay, I just want to reiterate a question Sam brought up, because I think it's a good one just to recognize. If you look at the overall reaction, so the overall's there at the top, or you may have written it again just in practice, okay? O2 is a reactant, but O2 does not show up in my overall rate law. What does that mean about O2? It's a reactant because it's in the overall, but it's not in my rate law. Adam, what are you going to say? Yeah. So this is another way in which we have found that this is second order and O2 must be zero order. The amount of O2 doesn't affect how fast the rate goes. It is a reactant, but this is why you can't just look at a reaction and write a rate law. Because an overall reaction doesn't show you what's actually affecting how fast or slow it goes. Yeah?
So like that rate, so does that mean that every time you put NO, the reaction is going to go 4 times as fast?
Yes.
Okay.
Yep, so the more NO I put, the faster the reaction will go. Yep, no, great connection. All right, now let's get to slow step, not first. All right, so do this for me real quick for 2 more smiley faces. We have steps, so we can write rates of steps. So write me the rates of these steps off to the side real quick. So write me the rates of those steps.
Oh, I thought you meant like to the This is just for each individual.
All right, if you have those on your paper, have 2 more smiley faces.
Would you do 2 for step 1 because it goes back and forth, or?
I'm glad you understand it goes back and forth, Macy. But for now, we're just looking at the rate of the forward.
Okay.
So technically, you could write a rate for the reverse, and then that would be the other one. So, and that will come into play here. Now, which step do we care about?
Slow.
The slow step, right? The slow step is the rate of the overall. But when the slow step comes second, we often have a problem where one of the things in the rate law is an intermediate. And you can't have intermediates in overall rate laws. So we can't do what we just did and say, oh, well, this is the overall. Here's the problem with having an intermediate. What is an intermediate?
It's a product that goes as a reaction.
Yeah, so it's something that's made and then gets used up, which means you can't measure, so brackets are concentration. You can't measure the concentration of it because it's made and then used and constantly changing. And in order to have a rate law, we need numbers we can actually plug in so we can use the rate law to find the rate. So our goal here is, it's still about the slow step, but we need to substitute out the intermediate for something that is equivalent to its concentration. Yeah, Connor?
Are we able to substitute out NOBR for NO plus BR?
So this is where something that's key about the step above, right? So did everyone notice that the fast step before has this double-headed arrow that we don't see tons yet? We'll see it more as we keep going throughout the year. But the idea of this is what's happening, right? So if I were to draw my graph, here's how I visualize it. Okay, so if the slow step is second, what does that mean about my hills?
Real fast. It's gonna go low.
Good. So we should have a little hill and a big hill, right? Something like that. Okay? The reason why the fast step before the slow step has the double arrow is it's kind of like the reaction's going like this.
Oh, that's good.
Right? It's like the roller coaster goes up and then back down, and then up and then back down, and then up, back down, right? Because of that, it's an equilibrium is what it's called. That's what the reactions are called when they go both directions at the same rate. So the rate it goes forward is equal to the rate that it goes back. So what we can do, I'm going to go to the next one just so I have a little bit more room here. If you turn your page over, I've actually copied those same equations again if you want to do this on the other page, or you have space at the bottom, you can do it there too. So the overall rate, right, should be equivalent to the slowest step. But we need to substitute the intermediate. Like Connor said, since this is at an equilibrium, what we can say is that NO BR2 is equal to NO BR2. Because they're at the same rate, and so the products are going to equal the reactants. Yeah, Eli?
So then when you rewrite it on the slower, would it be NO2, BR2?
So this gets plugged in for all of that, and then we are actually going to combine the like ones, because we have two NOs, right? So the true overall rate is going to be K NO squared, and then BR2. So that is your final answer. So when the slow step doesn't come first, you just sometimes have to do some rearranging to get the intermediate out of the rate law. Yeah, Eli, then Connor.
Would there be some problems like that won't like state the fast and slow steps? Will we have to figure that out? Or no?
The only way I could see them having to do that is they give you a graph. But besides that, they'll tell you. Because that has to be gained from the lab. Like you do a lab and see which step and how fast and slow they take. So, good question.
So
Yeah.
what happens if like the first step, the fast step,
Yeah.
isn't a forward and backward reaction?
It always will be.
Okay.
Yeah, good question though. So yeah, whenever the slow step isn't first, the steps preceding it always form an equilibrium because it's waiting in a sense for the slow step to happen. So it just goes back and forth.
So the slow step will slowly consume that NO2.
Yes. Yep. Good question though. Sydney, did you have a question?
Why isn't it BR squared?
So I substituted this into here, right? And so we just have one BR2.
Why is there two O's?
Because so this one had an NO, and then we substituted in another NO and then combined them together. Yeah.
So is the fast one always a forward backward reaction because it's easy for that reaction to happen?
Yes. Mm-hmm. Yeah. Yeah, Norm.
So how come separating the NO and the BR2 like doesn't change the equation entirely? Now you have like a separate thing.
So tell me if this isn't what you're asking. So the brackets are concentration, right? And so what this is because it's at an equilibrium, the concentration of these two is equivalent to the concentration of that together. So their individual concentrations are equivalent to the concentration of the intermediate that it's making.
Oh,
So that's why we can set them equal to each other, because it's like measuring concentration.
oh, okay.
Does that kind of make sense?
So it's because of the equilibrium. Like if it wasn't an equilibrium,
Yes.
then that cannot.
You could not do this if it was not an equilibrium.
Okay.
Yeah, at all. So
If you had 3 steps and the third step was the slow step, would that mean step 2 has to have the double arrows?
yes. Now those exist where you have 3, 4, or multiple steps, and the slow step isn't just the second. I've never seen it where on the AP, and once again, you should probably never say never in AP Chem because I feel like they like listening to me, right? And then they put it on a test. But in that case, you might have to do like 2 substitutions possibly, like with both of the fast steps or something. The biggest thing is that your final answer should have removed the intermediates. So, any other questions on that? Now, let's say hypothetically here, I'm just going to put this in just so you can see a different scenario because I should have found an example, but I didn't. If you had more than one product, okay, so let's say hypothetically that this had like plus A or something as a product. That would mean here you would also have A. And for our example's sake, we're going to say that A is a product, so it's not an intermediate that goes away. We still have to isolate just NOBR2. So make your rate law look a little strange, but you would have to divide the A to the other side and then substitute that whole thing in. So your overall rate law might have a fraction in it when you do this substitution thing, and that's okay. It looks a little weird, but that's also how you get like negative rate orders and things like that. So
Why don't we have to do the stoichiometry while we're doing this?
the stoichiometry comes in with writing the individual rate laws. That's kind of where the stoichiometry is, right? Because these rates were determined from the stoichiometry, so that's kind of where it plays its part. But yeah.
Would you, for the rate law with A,
Yeah.
would you then still combine the NOs or would you keep them separate?
Yep. So if that's how it was, my final answer would be this, with just A on the bottom. So, yeah, Sid.
Do you have a catalyst in your law, or is this the same thing?
Nope, you can. Yeah, because if the slow step is first, you often will have a catalyst in your rate law. So catalysts, yes, can be in a rate law because they will affect how fast it goes and they can be measured. That's the key thing why we can't have intermediates is you can't measure those. But a catalyst I put in. And so I can measure how much I have to do the math with it. So, yeah, Andrew.
So when you have the NO2, you combine them,
Yeah.
and then if the product divide the second, like, NO in step 2? Or would you have to separate those and then divide only one of those NOBRs? Does that make sense?
No, I lost you.
So, I think it'll be.
Do you want to come show me? Okay.
Um,
Are you saying like if A was NO instead of like an A?
No, A is just going to be A. It's just that because we combined this NO from our other one, would the rate be rate equals K NO BR divided by A, and then another NO, because we combined them, and this is being divided, or the step 1's rate law is being
I see what you're
divided by
saying.
A.
So, oh, I see what you're saying now. Good question. So since it's all multiplication and division, right?
Mhm.
Which for order operations doesn't matter.
Okay.
And so you still would combine them together. So this mathematically is equivalent to that.
okay.
So good question though. Okay, with your table, buddy, try practice problem 5.9. Ready, set, go. I know, I just some sort of official stamp.
Speaking of official things, have we found a smiley face?
No. I'm happy.
Or if we just offer a smiley face reward for anybody who finds it. Oh, yeah.
So wait, so this one and I'll be like, oh, sorry, you have it. Why would it be that way? Yeah, because if I have these
Okay, if you have that, have a smiley face. Question, Hannah? Ooh, good question. Okay, everyone listen to this. Hannah asked if we had, what would we do if we had more than one slow step? And the answer is actually I'll only ever have one. It's kind of like it doesn't matter, because it's like always a comparison of which one is the slowest is always labeled as slow, right?
What if they're the exact same speed?
The bigger the hill is always classified as the slow one, because once again, it's kind of the idea of once you have enough energy for that, anything else is going to go on its own. So, good question though.
What if it's like the same, like takes the same amount of energy?
Ooh, if you had two identical speed slow steps.
Yes.
I'm,
Would you give up? Or
yep.
would you just
I don't know, I've never seen it before. Once again, I wouldn't say it doesn't exist. Well, here's probably what I'd say in real life circumstances. So, the first day of this unit, we learned how to find rate laws from data, right? So in this case, if that was the case, a mechanism would not be the best way to find the rate law. We actually, by the end of the unit, we're going to have 3 ways to get to rate laws. So the first day was the data, where you compare double, dozen double, stuff like that. This is the second method, and then on Wednesday we'll learn a third method.
Oh, which one's the easiest?
So,
It's gonna be one of the fancy.
is that what I said?
She said Thursday.
I don't know what I said. Yeah, Ben.
I think you did great.
So it's, we look at the slow step, right, and write its rate.
Right.
And then that is equal to
But this is an intermediate, so this can't be your answer, so you substitute those into it. So I guess another thing that doesn't really matter, so you look at the slow step, anything past the slow step, you can kind of ignore, right? There could be like 10 fast steps. It's just about the slow step and then any that come before it.
Oh, okay.
So does that help? That answer your question?
So basically you do the rate for the step before the slow step.
Will you substitute it in for the slow step?
Okay, that makes sense.
Yeah.
So let's say if there were like 5 other fast steps happening before the slow, but say that the like NO2 F2 was used in like step 2 and then the slow wasn't until step 5, but then it mentions NO2 F2. Like, does it still count as an intermediary or?
Yep, if it's made and then used, even if it took a few steps to use it up, it's still an intermediate and you'd have to substitute it out still. Yeah, that's a big takeaway. You can't have intermediates in an overall. So if there is an intermediate in the slow step, you got to find a way to substitute it out. So.
Why isn't there a way to measure the intermediate? Just because we go back and forth?
Yeah, because it's getting made and then also used.
But
Right?
If I wanted to, I could just do like one, if there's a way just to do one step and then measure it, and then go back and then do one of the later steps and then say, okay, this is how much we have now, and then let's use it, and then this is
Yeah.
how much we got used.
Yeah. It'd have to be like a very, very controlled lab setting though, right? So, yeah.
How would we solve one of these problems if it doesn't say like which one is fast and which one is slow?
It will tell you. So I know I forgot to tell you on your paper, so it was told you up here. Yeah.
My idea, was it the arrow?
It will tell you. Yeah, because otherwise that information has to be determined in a lab setting. So on just a paper, there's no way of knowing. Unless they gave you a graph. I could see them doing that, like giving you a graph,
Well, the arrows.
and then from the graph. The arrows also should help, right? Because fast are always equilibrium. But yeah. Yeah.
We only have 5 minutes left.
Thank you. Okay, last thing, let's draw some pictures of our graphs. We've talked a lot about them, but let's have them in labels. Okay, so this first box right here, we want to draw just an example of a 2-step reaction where the slow step is first and the delta H is negative. So first off, with our steps, what does it mean if the slow step is first? Good. I love how I wasn't even looking, but I knew what you meant just by that sound effect. So we need a big first hill and then a smaller second hill. What does it mean if the delta H is negative? The change in energy is negative, so it's releasing energy. So what needs to be lower? So the products need to be lower than the reactants. So if I'm doing a negative delta H, I always start my reactants higher because they have to end lower.
Wait, so it's
All right, and then we're doing what? Slow step first. So I need a big hill, little hill. There's obviously various things, but the big takeaways are this needs to be bigger than that.
yeah, that's the thing I don't know.
Okay, so this is step 1, this is step 2. So the activation energy of step 1 needs to be bigger than the activation energy of step 2. Then the delta H is from here to here, and it's negative because the products are lower than the reactants.
So how does that make it different than
So do this one for me, then we'll check it. Okay, for a smiley face, draw a picture of this. So 2-step reaction with a slow step second and a positive delta H. So fill that box in and then we'll check it. Slow step second. Set your pencil down when you're done drawing your graph.
Random question. What's the most amount of smiley faces you've ever had, like once you
Like at the end of the year?
Yeah.
20 people.
The one I think about the top of my head was like 130.
Wow. Are they all legit?
Yeah, I trusted them because I didn't have to use a single one all year long. They were always there in class. They were always asking questions, so and like participating and stuff.
Oh man, I just drew Bart Simpson.
Something like that is what you should have. Okay? Okay, have a smiley face if you have that. Okay? Now,
Oh yeah. You could break the record. I just broke the record. Oh yeah. Based off
okay. Now, I've seen a student for these stipulations draw something like that. What's wrong with it?
Evaluation 1.
Yeah, make sure it's not about the height of the hill for just the y-axis, right? It's from the bottom to the top. And that's actually bigger, right, than that one. So just be careful when you're doing it that you're measuring the actual activation energy and not just like how high the mountain goes. I also would not make them look too similar, right? Like if this is what the question is saying, don't make the grader have to pull out a ruler to see which one's bigger. Okay, make it obvious of which one's the slow step and which one is the fast step. So, questions on that? Okay, all right, very good. You got your homework, 5.8, 5.9, that's practicing the rate law mechanism stuff. And then some AP quizzes, a little bit of reading. 10 is graphs, so yes. Hold off on 11, because that's catalyst, which we didn't get to. So you guys, B6 needs to do 11, but you guys don't need to do 11.
I will remember this because it looks like Bart Simpson. Doesn't it, like his mouth?
I don't see it.
So here's his mouth, right? You draw his head right here. I feel like I've had a library.
Oh, like he's lying down?
It's like hair.
Oh yeah, I can, yeah, I can see it, I can see
I'm
it.
referring it to Bart Simpson.